Hey folks, how y'all doing? I hope y'all had a fantastic break. It's good to see y'all back, such as it is. What we're going to do for the next 5 class periods is just get ready for the final exam. Um, Bring questions. Let me know what kind of things y'all want to do. What I'm going to do today is work with you through the spring 2016 final exam. Um, this is an old final exam. We're going to just do it start to finish together. And let's see how it goes. Before we start this, I've got a couple of announcements. I hope that these will be um, not too surprising. The final exam is scheduled for 11:05 on Tuesday, December 15th. It is a common departmental final. The first half of it is a multiple choice exam. By department policy, you have to take the exam at that time. 11:05 on Tuesday. It won't be available before then. And so whatever time zone you happen to be in right now, make a plan to be awake and online at 11:05 Virginia Tech time on that Tuesday to take the exam. You'll have 50 minutes to work through the exam. Those of you with ADA or SSD accommodations, you'll have 100 minutes to work through the exam, but you'll still start at 11:05. You do not have to use a lockdown browser, and you are allowed to use your notes on the exam. My understanding is that you're not allowed to use a calculator, but I don't know um, how they would enforce that. But the plan is that you should not use a calculator. And even though it's open notes, the fact that it's only 50 minutes and you have 10 to 12 questions to work through during that 50 minutes, you won't really have time to refer to your notes. If you are having to go back and look something up, you are not going to finish. That's just a an unfortunate truth. You want to be prepared to take this exam without your notes. You could use them if you have to, but if you have to, you won't finish. The second part exam is free response. The timing for that is a little bit looser. You can take it immediately following the multiple choice exam if you want to, or if you want to take a break in between, that's fine. The second part exam will be open until 9 p.m. You cannot take the free response part first. You can't take it in the morning and then take the multiple choice part. You have to take the multiple choice part first. You have to take it at 11:05. But then after you're finished with the multiple choice part, you have several hours in which you can fit a window to take the free response part of the exam. Each part weighs 50% towards the final grade. And so that's what's going to be happening on Tuesday the 15th. So that's 2 weeks and 1 day from today. And so we've got time to get ready for this. Let's go ahead and get started. So all of these questions came from the 2016 final exam. I've put a link on Canvas for where you can find these old finals. Start working through them and bring questions. So let's look at this one here. Number 1. Let's evaluate this integral, cosine of x squared dx dy over these boundaries. Now the first thing I see is that the integral of cosine x squared is hard with respect to x. It's very hard. But the cosine of x squared dy is easy, because this is just a constant with respect to y. And so my goal is to switch this and do the dy first. And to do that, I need to draw a picture. Of the boundaries. Okay, So my boundaries are y equals 0, y equals 1, x equals 2y, and x equals 2. So y equals 0 and y equals 1 are these two horizontal lines here. X equals 2y is a diagonal line with a slope of 1/2. And x equals 2 is this vertical line here. And the arrows in the x direction enter at 2y and they leave at 2. And so this is the region that we're looking at. This is a region that is bounded by all four boundaries. So if we keep these same boundaries, but we set this up in the order dy dx, my smallest and largest x values are 0 and 2. And now my arrows will be traveling in the y direction. And they'll enter the shape along the bottom, which is at y equals 0. And they'll leave the shape along the diagonal line, which is x equals 2y. But that's the same thing as y equals 1/2 x. Same line, I'm just writing it in terms of y instead of terms of x. And nothing changes in the middle. This is still cosine of x squared. The only time we change the middle is when we're switching geometry from rectangular to polar or from rectangular to spherical. But we're not doing any change in geometry. We're still doing rectangular coordinates here. And now this integral is much easier to work out. The integral from 0 to 1/2 x cosine of x squared dy is equal to cosine of x squared y evaluated at 0 and 1/2 x, which is equal to 1/2 x cosine of x squared minus 0. And now we have to integrate this from 0 to 2. I'll pull the 1/2 out front. And this works nicely with a u substitution. Let's do the u substitution here. We're going to let u equal x squared. And then du will be 2x dx. And so x dx will be 1/2 du. When u is equal to x squared, 0 squared is 0, but 2 squared is 4. So my boundaries change from 0 to 4. This 1/2 is the original 1/2, but I get a 1/2 out here. 1/2 cosine of u du. And this 1/2 came from there. All right. The integral of this integral of cosine is sine. The 1/2s combine, I get a 1/4 sine of u. And now I'm going to plug in 4 and 0. And when I plug in 4, I get 1/4 sine of 4. I don't know what the sine of 4 radians is. But the sine of 0 is 0. And so this is going to be the answer that I'll get. And that's choice B. All right. Let's move on. Number 2. Which of the following is an equation for the plane that goes through the point 1, 1, -1 and is parallel to the plane x minus y plus z is equal to 3? So I have these two planes that are parallel to each other. which means that any vector that is perpendicular to this plane will be perpendicular to this plane also when it pops through there. And therefore, the left side of the equations should be the same or maybe negatives of each other, because we could also use the normal vector that goes this way. And so this answer is wrong. And this answer is wrong because I have positive x and negative y here, but positive x and positive y here. This looks plausible because this is exactly the same. X, negative y, positive z. X, negative y, positive z. But this is also possible because it's the reverse of this. So these two are possible. So the second question is, which of C and D contains the point 1, 1, negative 1? Well, choice C is negative x plus y minus z equals 1. That would be negative 1 plus 1 minus negative 1 equals 1, and that checks. Negative 1 and positive 1 cancel, and minus a negative 1 becomes positive 1. Whereas if we look at D, x minus y plus z equals negative 3, this would be 1 minus 1 plus negative 1, and the 1 minus 1 cancel. This does not equal negative 3. And so the correct answer has to be C. All right. Let's keep going. Let's evaluate this integral here. Wow. Okay. So what I'm going to do first is see if we can convert this into polar. Here are my two clues for polar. Two clues why we should do this in polar. One is that every answer has a pi in it. Every single answer choice has a pi in it. And the second reason is I see a lot of x squared plus y squareds up here. And I know that x squared plus y squared simplifies to just r squared. And so I see a lot of this. So let's try to do this in polar and see what happens. So we're going to draw a picture. So for the first region, my boundaries are x equals 0, x equals the square root of 2, y equals 0, and y equals x. And so that goes from x equals 0 to x equals square root of 2. Y equals 0 is this line here, and y equals x is this diagonal line here. And it'll go up to square root of 2 also, because y equals x. And we are entering the region at 0 and leaving the region at square root of x. So entering along y equals 0, which is down here, leaving along y equals square root of x, that's got to be this piece right here. All right. But then we have this second piece that goes from x equals square root of 2 to x equals 2, y equals 0, and then y equals the square root of 4 minus x squared. So we're going to go out a little further from x equals 2 to x equals from x equals root 2 to x equals 2. Y is still going to start at 0. But the top boundary now is this boundary, which is the same thing as y squared equals 4 minus x squared, or x squared plus y squared is equal to 4, and that's a circle of radius 2. That's this boundary here that's part of a circle. So we're adding this region plus this region. And this is a piece of a circle where the radius goes from 0 to 2, and the angle goes from 0 to pi over 4. Okay? So let's try setting this up in polar. We always want the radius on the inside. So we'll put 0 and a pi over 4 here, 0 to 2 here. Square root of x squared is plus y squared, sorry. It says square root of x squared plus y squared. It says x squared plus y squared is r squared. Then the square root of x squared plus y squared is just r. But we gain an r when we convert to polar. So this is going to be r squared, dr d theta. We'll do the inside integral first. The integral from 0 to 2 r squared dr will be r cubed over 3 evaluated 2 and 0, which is 8/3. Then we're going to integrate that from 0 to pi over 4. There's not even any trig here. This is just 8/3 theta evaluated pi over 4 and 0. And so we get 8/3 times pi over 4 minus 8/3 times 0. The 8 and the 4 reduce and leave me with a 2. And so we end up with 2 pi over 3, which is choice A. Oh, wow. Okay. Let's move on. Number 4. Which of the following statements is true about this limit here? Okay. So 3 possible cases where it doesn't exist, and 1 case where the limit is equal to 0. Okay. So let's look through these possibilities. One is that the limit is x stays the same, but y is being replaced with 0, says that limit doesn't exist. But if we replace y, so in choice A, y is replaced with 0, and that gives me the limit as x approaches 0 of x squared times 0 over x to the 4th plus 0, but that's just a limit of 0 over x to the 4th, and that's still 0. And so this is not true. This limit does exist. Okay? So let's look at choice C. It says that the limit as x of this limit, which we have already found is equal to 0, doesn't equal this limit. In this second limit, y is replaced with x squared. So let's look at what happens. The limit as x approaches 0. X squared times y would be x squared times x squared, which is x to the 4th, over x to the 4th, plus y squared would be x to the 4th again. And that's the limit as x approaches 0 of x to the 4th over 2x to the 4th, and that equals 1/2. And that doesn't equal 0. And so these two limits are different, and therefore this limit doesn't exist. So we started checking the limit doesn't exist things, and we found an answer that didn't work. Let's look at D quickly. The limit doesn't exist because the function is undefined at 0, 0. That's not correct. The limit doesn't have to be defined at the point that we're approaching. It just has to be defined around that point. As excuse me, that's just part of the definition of how limits work. The function has to be defined around the point we're approaching, but not at the point. And then this limit is 0 because this limit is equal to 0 for all values of k. This only considers straight line paths where y is equal to a multiple of x, and not curved paths like y equals x squared or y equals cosine x or sine of x. This is not enough. The definition requires that this limit has to approach 0 for every path that goes to the origin. So not enough paths. So the answer really is C. Okay. Let's move on. Number 5, find the unit tangent vector to this curve. So the definition is that the unit tangent vector is equal to the derivative of the trajectory divided by the magnitude of the derivative of the trajectory. So we'll need to find the derivative first. The derivative of this trajectory will be cosine of t, comma 1, comma negative sine of t. And we're told that t is equal to 0. So cosine of 0 is 1. 1 sine of 0 is 0. And the magnitude of that vector, you could do this in your head. This is the square root of 1 squared plus 1 squared plus 0 squared, which is the square root of 2. And so the unit tangent vector is 110 divided by the square root of 2, or 1 over the square root of 2, 1 over the square root of 2, and 0, which looks like it's choice of D. All right. Let's keep going. Number 6. A ball is thrown into the air with an initial velocity of 3I plus 8k, which is a vector 3, 0, 8. There's no j in this vector. And the acceleration vector is 8j negative 16k. How far away is the ball from its initial position at t equals 1? Okay. So let's start with the acceleration. Your velocity vector at time t is the integral of the acceleration vector, dt. And we're told actually that this is not just initial acceleration, this is constant acceleration at all times. So the integral of this is going to be c1 8t plus c2 negative 16t plus c3. And since we know that at time t equals 0, we get 3, 0, 8. C1 will be 3, C2 will be 0, and C3 will be 8. And so your velocity vector is 3, 8t, negative 16t plus 8. And so now your position vector is the integral of your velocity vector. And so that's going to be the vector 3 plus a constant. I'm going to reuse C1, C2, C3. That's kind of bad style, but I'm going to do it. And then integral of negative 16t is 8t squared. The integral of 8 is 8t plus c3. We're not given a coordinates for the initial position, but it doesn't matter because we just have to figure out the displacement from the initial position to the final position. And so we'll set the initial position equal to the origin. So using r of 0 equals to the origin gives me that C1 is equal to 0, C2 is equal to 0, and C3 is equal to 0. And so this vector at time t will be just 3t. I left off the t here because I write t in a plus sign, and I think my brain substituted for both of them. 3t, 4t squared, and negative 8t squared plus 8t. All right. At time 0, we're at the origin, but at time 1, we're at 3 times 1 is 3. 4 times 1 is 4. Negative 8 times 1 plus 8 times 1 is 0. And so how far away is the ball? It would be the distance is the square root of 3 squared plus 4 squared plus 0 squared, which turns out to be exactly 5 units. Okay? Let's keep going. Number 7. 2 right circular cylindrical storage tanks, A and B, have volume pi r squared h. So they're right circular cylindrical storage tanks. So here's A, and here's B. And they have a height of 25 meters and a radius of 5 meters. The radius of tank A is increased by a small amount. So we have a slightly wider tank now. Where the radius is now 5 plus some change in the radius. But the height of tank B is increased by the same small amount. So tank B is now a little bit taller by, in this case, delta H, but delta H is equal to delta R. So which of the following statements is true? The volume of tank A increased approximately 10 times more than the volume of tank B, and the volume of tank B increased approximately 10 times more than the volume of tank A. And 5 times more and 5 times more. So let's look at what's happening. The volume is pi r squared h. The change in the volume with respect to radius is 2 pi rh, where r is 5 and h is 25. And so that's 250 pi. VH is equal to pi r squared times 1, which is pi times 5 squared, or about 25 pi. What this number says is this volume went up by approximately the change in the volume is 250 pi times delta R, and this, the change in the volume, was about 25 pi times delta H. So change in the volume is the derivative with respect to r times the amount of the change in r. And the derivative in the change in the volume here is the derivative with respect to h times the change in h. And so tank A got bigger by about 10 times as much as tank B did. And so that's choice A. Okay? All right, let's look at choice A, problem number 8. Rewrite this triple integral in dx, dz, dy order. All right. So we're looking at a triple integral now. My boundaries are y equals -2 and y equals +2. X equals to, or z equals to, sorry, y squared and z equals to 4. And x equals to 0 and x is equal to I am reading this backwards. Sorry. These really were x and x up here. And these are z. Z goes from 0 to 2 minus x over 2. All right. So -2 to 2 goes from back here to here. So those are some of my boundaries. X goes from y squared to 4. So here's 4 is going to be out here. And x equals y squared is going to be a parabola that opens in the x direction. Okay. So that's what the base looks like here. And then z goes from 0, which is down here at the base, to 2 minus x over 2. So when x is 0, z is 2 minus 0 over 2. When x is 1, z goes down to 1.5. When x is 2, 2 minus 2 over 2 is 1. When x is 3, we go down to 1/2. When x is 4, z goes down to 0. And so that's what the shape looks like there. And so this is the kind of region that we're looking at. It's curved along this side, straight along this side, and then there's a flat top connecting these points also, okay? All right, so we have to set this up now in the order dx, dz, dy. So y is still going from -2 to 2. I forgot to draw the other side of this. Sorry. There you go. -2 to 2. All right. This time, we are going to set our wire in the ZY plane. That's this plane here. It's going to move in the Z direction, but the wire is parallel to the y-axis. So the wire is below the shape. As we pull it upwards, it enters at z equals 0, and it leaves along this flat surface where we have to do a little bit of math here. Z is equal to 2 minus x over 2, but x is equal to y squared. And so this is 2 minus y squared over 2. All right. And then as our arrows travel in the x direction through the shape, they enter along the parabola at the back, which is x equals y squared, and they leave along this flat surface here, which is this equation here. But if z is equal to 2 minus x over 2, I have to solve this for x. So I'm going to write this as add the x over 2 to this side and bring the z over to this side, 2 minus z, and then multiply by 2. X is equal to 4 minus 2z. And that's the same equation as the front of this surface, but written in terms of x instead of in terms of z. And so we get negative 2 to 2, 0 to 2 minus y squared over 2, and y squared to 4 minus 2z. That's choice A. All right, let's keep going. Number 9. Let's find the maximum rate of change for this function at the point 2, 0. The maximum rate of change is always equal to the magnitude of the gradient vector. So let's find the gradient vector. F of x is equal to 2x minus e to the 2y, and f sub y is equal to negative 2x e to the 2y. And at 2, 0, this is going to be 2 times 2 is 4. E to the 0 is 1. 4 minus 1 is 3. This is going to be negative 2 times 2. That's going to be negative 4 times e to the 0 is just negative 4. And so the gradient vector is 3, negative 4. And the magnitude of the gradient vector is the square root of 3 squared plus negative 4 squared, which is equal to 5. And that's the maximum rate of change. Okay. Number 10. This is a problem we've seen before. We did a problem like this in WebAssign. Let this be a differentiable function of x and y. Let g of r and s be this function here. Use the table of values to calculate g of r at 2, 1. So this tells me that r is equal to 2, s is equal to 1, x is equal to 2rs, which is equal to 4, and y is equal to 8s minus 2r. 8 times 1 minus 2 times 2 is also 4. And so x comma y is equal to 4, 4. And so since this table is headed x comma y, we want to use this row and not this row. And so our diagram is that the function g of rs and the function f of x comma y are the same function, but they depend on x and y, and then x and y both depend on r. They also depend on s, but the s is not what we're calculating because we're calculating g sub r. And f sub x is 2, and f sub y is 3, and we got that information from the table. And then x sub r, x is 2rs, so x sub r will be 2s, which is equal to 2. And y sub r is going to be negative 2. And so g sub r is going to be 2 times 2 plus 3 times negative 2, or 4 minus 6, which is negative 2. All right. 3 more. Let's get through them. All right. Number 11. This is a challenging theory problem. The figure below, straight lines represent the level curves of a function of f. So this line and this line, these are level curves of f. The ellipse is the constraint g. The arrows are labeled. They're the gradient vectors for the function. And one of the things we know is that the gradient vectors are always perpendicular to the level curves. So the gradient of f is perpendicular to the level curves of f. So we have that. We also know that the gradient vector for the constraint is perpendicular to the level curves of g, but the level curve of g is an ellipse because everywhere along this curve, this is equal to 0. And so the constraint stays level along this curve. And so that means that the constraints are, the gradient vectors are perpendicular to the ellipse. They all pop out of the ellipse at all of these points. And so at point A, the gradient vector is going to be pointing straight out this way, perpendicular to the ellipse. But at point B, the gradient vector to the ellipse is going to be pointing in this direction. The maximum occurs when the gradient vector for f and the gradient vector for g point in the same direction. If they point in the same direction, then the only difference between the two vectors is some scalar, which we call lambda. That's where that lambda comes from in the formula. So B is the only point here where the gradient vector of f and the gradient vector for g are pointing in the same direction. And so the maximum value of f of x, fxy could occur at point B, but it cannot occur at point A. That's choice A. All right. So let's keep going. Number 12. The absolute minimum of this function over the line segment x equals 2 with 0 less than y less than 2. Okay, let's see what that says. So the line segment is x equals 2. That's a vertical line with 0 less than y less than 2. So this is our segment here. Okay. All right, so let's look at this function here. The interior of the line segment will just be replace x equals 2. F will be equal to 2 squared, which is 4, plus 4y squared minus 4y. The derivative will be 8y minus 4. we set the derivative equal to 0, we get 8y equal to 4, and so y is equal to 1/2. And so right there is going to be a critical point for this function. X is equal to 2, y is equal to 1/2, z is equal to 2 squared is 4. 4 times 1/2 squared is plus 1, that's 5. 5 minus 4 times 1/2, 5 minus 2 is 3. So we get z equals 3. But we also have to check the endpoints. And those are 2, 0, and 2, 2. So at 2, 0, and 2, 2, we get, at 2, 0, we get 4 plus 0 plus 0. And at 2, 2, we get 4 plus 16 is 20. 20 minus 8 is 12. The minimum that we get is 3. All right. Last problem. Rewrite this triple integral in spherical coordinates. And this is already given to us in cylindrical coordinates, not in rectangular coordinates. So it's already in a polar system. We have to convert it to a different polar system. Oh, wow. So let's draw this out. My boundaries are theta goes from 0 to 2 pi. R goes from 1 to square root of 2. And Z goes from negative square root of 2 minus r squared to positive square root of 2 minus r squared. All right. See if we can draw this. R equals 1 and r equals square root of 2 are two little circles, different radii, going all the way from 0 to 2 pi. This is saying, let's write this out, z squared is equal to 2 minus r squared, which is the same thing as r squared plus z squared is equal to 2. R squared is the same thing as x squared plus y squared. And so this is a sphere of radius square root of 2. The radius squared is on this side. So this is the end of the sphere. And so we're looking at a sphere with a hole cut out of the center. That's the problem, is that we're not integrating this part inside the hole. So our shape looks like, I don't even know if I can draw this. Like a sphere, but there's a hole that's cut out through the center. Okay? All right. So now let's figure out what's going on in our spherical coordinate system. Theta still goes from 0 to 2 pi. And unfortunately, that doesn't rule out any of our choices because they all go from 0 to 2 pi. So let's talk about what happens to phi. Phi starts out at this angle right here. And it ends at this angle down here, where it crosses in and out of this shape here. So let's draw a diagram here. The radius out from the z-axis is 1. That's the inside circle. But the radius of the sphere itself is square root of 2. And so by the Pythagorean theorem, this side is also 1. And so this is a 45-degree angle, or pi over 4. And then by symmetry, this angle down here is going to be 3 pi over 4. So pi over 4 to 3 pi over 4, which also doesn't help, doesn't get us anywhere. And then our last coordinate is rho. And so what happens to rho? Rho will end at square root of 2 if my arrows are moving in the direction of rho. They will end at the square root of 2, but they will enter along this vertical line here, which is the line where r is equal to 1, which is the same thing as, well, if r is equal to 1, r squared is equal to 1. So we can do that. X squared plus y squared is equal to 1. And in spherical coordinates, x is equal to rho cosine theta sine phi. And y is equal to rho cosine, rho cosine theta cosine. I'm messing this up pretty bad. Let's try this again. Rho cosine phi cosine theta, and y is equal to rho cosine phi sine theta. And so x squared plus y squared is going to be rho squared cosine squared phi cosine squared theta plus rho squared cosine squared phi sine squared theta, which is just rho squared cosine squared phi, and that equals to 1. And so rho squared is equal to 1 over cosine squared phi, and so rho is equal to 1 over cosine of phi along this vertical boundary, and that's right here 1 over cosine of phi. Took a lot of work to get to that complicated vertical line boundary, but that's what you have to do to get through number 13. Okay? All right. Bring questions. We'll have class at our regular time today and office hours at our regular time today. And I hope to see some of y'all. Take care.